Hey everybody, you'll notice at the top of the screen we're going to go through trigonometric applications today. So what we're going to talk about is how we apply our trigonometry to real-world situations, to different applications. I want you to take a moment and read the first problem. A small part of what we're going to do for every problem today is going to be to draw a diagram. So I want you to give problem 1 a read, and then on the left side of your page, let's go ahead and draw a diagram that would mimic that situation. Okay? I want you to try it on your own. Pause the video now. Okay, we're back. So if you were to go through, the problem says the angle of elevation of the top of a building is 70 degrees from a point 120 meters from the foot of a building. Okay, so if I was to draw my building, that would be my building. Now, quite often, people want to draw like a building. They want to put the ground on it. They want to put in windows. They want to do... Don't. Just draw what you need for a diagram, a functional diagram. So, like, if you even wanted to say, like, there's the top of the building. Okay, we're great. The question says that the angle of elevation of the top of a building is 70 degrees from a point 120 meters from the foot of the building. So if I was to come over to the left and choose a spot 120 meters from the foot of the building, and that's all I'm going to do, I'll clean that up a little bit. That is then 120 meters. Then it means that if I look forward, then elevate, so I'm going up, that angle would be 70 degrees. The question says, find the height to the nearest meter. So I need to find the height of the building. Now, there is something very important when we talk about trig applications. And I know that when I say this, it's going to sound really weird, but go with it, okay? When we say that we have a building is vertical. So you can believe that it's vertical. So we have a bit of a phrase where we say vertical things are vertical. And I know that sounds really weird, redundant actually, but it tends to make sense. If we have a building and we tell you that there's a building, then you can have faith that that building is vertical. What I mean by that is it is perpendicular with the ground. There is no, yeah, but what about if the building was leaning? Like, I don't know, there's nothing with that. Okay, if I want the building to lean, I will tell you that it's leaning. Okay, I have to tell you that. Vertical things are vertical. Now, the other part to that then is horizontal things are horizontal. And so what we mean by that is, if I have a building, then I know that the ground is perpendicular to it. If I want the building to be on top of a hill that goes down, then I have to tell you for all the same reasoning. So, when we say that you have a building, then that means that the angle it makes with the ground is a right angle. Okay, there you go. You are responsible for coming up with that height. Now that we have that diagram, I think you should be good to actually finish off the problem. Okay, I want you to pause the video and give this one a shot on your own. Okay, pause it now. And we're back. So you take a peek, and now with that diagram, really we've turned this into a mechanical situation. Can we now interpret and problem solve our way through? So if I look at that 70-degree angle, my height is opposite, the 120 is adjacent, and that is the sides of a right triangle, so I can use my SOHCAHTOA. So I could say then that the tan of 70 degrees is height over 120. There's your mechanics, and we should be good to solve. You should be quite comfortable to know you have to show me the exact height of the building, 120 tan 70, Then we're going to push some buttons and we're going to get an approximate for it. So when you go through and you push buttons, the problem says find the height to the nearest meter. So this is the only time I round. I'm going to round to no decimal places. And so my calculation would put me at like 329.6.7. Since I'm going to round it to the nearest meter, there I go, 330 meters approximately. Make sure you have your approximate symbol. Make sure you have your units on there. And there we go. Okay, hopefully not too bad for the first application. And we can kind of see where we're going for the day. Okay, let's jump into the next problem. Okay, you can see problem 2 on your screen. I want you to do the exact same thing. I want you to give the problem read, and then I want you to draw the diagram. I am going to ask you to stop after you've drawn a fully labeled diagram. Just stop right there. I'm not going to let you go too far in the wrong direction, but we want to see where our instinct takes us. Okay? Try it on your own. Pause the video now. Okay, we're back. So it says from the top of a fire tower, so you'll notice the top of my fire tower looks an awful lot like the top of my building, right? I just want a functional diagram. It says the angle of depression of a cabin is observed to be 25 degrees. Find the distance from the cabin to the foot of the tower. So like I have like a cabin over here, and this is about as much detail in my picture that I'm going to draw, but that blue cabin. So it says find the distance from the foot of the tower to the cabin. So that is this distance. I'll call it X. If the tower is 200 meters high. It's a tall tower. Okay. I think we should be good when it says the angle of depression. So somebody's looking all the way down to the foot of that cabin. The fire tower is a building, so it's vertical, and it makes a 90 with the ground that's horizontal. There we go. Okay. I want to highlight probably the most common mistake that's going to arise when we talk about angles of depression. And this is why I asked you to draw the diagram and then stop there. I would bet, like a lot, that if I were to see your page right now, I would have many, many, many of you with 25 degrees right there. And I need you to understand that that red is incorrect. Okay, I think it happens primarily because we get used to solving all these triangle questions and we want an angle inside the triangle. So we're tempted, okay, I want to label that 25 in there. But we've mislabeled the angle of depression. So I want to make sure that we're good with both of our situations. I'm going to go back to like the previous problem. I'm not going to flip to the problem, but you can see it on your page. The way that we measure angles, here's my big diagram. Here's my wonderful artistic person. There's my stickman. That stickman always looks out from neutral position. So I want you to imagine that someone is standing there. They are not looking up. They are not looking down. They are looking parallel with the ground. Neutral position. If I then asked you to have an angle of elevation, then I hope that the word to you would say, hey, that person is then going to look up. They're going to elevate, and that creates their angle. You can see problem 1, that's how we got our angle of elevation of 70 degrees. Okay. You might be able to see why that 25 degrees was in the wrong spot. So let me get rid of that green and let me do the same thing now. Now what I want is the angle of depression. So I start looking straight out, neutral position, and then if I'm going depression, I'm going down. There is my angle of depression. You can see it with that green angle marker. So maybe you can look back on the diagram now and we can see where the mistake was. Remember, angles are always started from neutral position. So if I get rid of my wonderful artwork, then what you might see is the person standing at the top of the tower begins their angle by looking straight out. If it says angle of depression, then that is their angle of depression, which is 25 degrees. And notice, it is not inside your triangle. Easily the most common mistake. Okay, since we've got that, and I assume that your trig is okay after this, I want to talk to you about a couple ways that we could go through and solve this problem. First off, I think we know that for us to find x with one side of that triangle labeled, we're going to want an angle inside the triangle. So this becomes your option, and I'm going to use some colors to do it. If you want to, when you see that 25-degree angle, we should be good that vertical things are vertical and horizontal things are horizontal. So if the person's neutral position at the top of the tower is straight out, then it should make an angle that is perpendicular with the fire tower. So if the red angle is 25, then the angle inside the triangle has to be 90 minus it. The complementary angle, it's 65 degrees. And you may choose to use that 65-degree angle to solve for x. I'm going to do that solution in orange off on the side. From the 65-degree angle, I've got opposite, I have adjacent, there's my tan again. So the tan of 65 degrees is going to give me x over 200, and you should be good to finish off that problem. Multiply out your 200, and now calculate and round as required. Okay, there is another way to solve that problem though. I want you to notice that you had to do a little bit of work to calculate the 65. But then if you look at the orange equation, that became like the easiest equation to solve. Just multiply out your 200. The other way is really like I don't do much work early. I'm going to put in green that I could find the angle down at the cabin. And you might be able to see why on the diagram. I'm going to draw some stuff on the diagram. Please don't draw this on yourself. But if you take a look at my original neutral position, which has to be parallel with the ground, horizontal things are horizontal. Then what my purple dotted line represents, yikes, was that messy? Can you see your Z pattern in there? That the angle up at the top, my red angle of 25, has to equal my angle in the opposite, or the correct terminology, alternate corner. That could be a way that I get my 25 degrees inside my triangle. Okay, I'm going to get rid of all that green. And now I want us just to take a peek and say, well, what if I wanted to use that 25? Okay, you may wish to use that 25 because notice you didn't have to calculate the 65. What do you have to show me to show your reader of your solution that you use Z pattern? If you show your neutral sight line and the ground as parallel by just putting on those green arrows, then you can label that bottom right corner as your 25 degrees and then feel free to use it. So you'll notice I didn't have to do much work at the very beginning. I already had the 25. What that becomes then in terms of a solution, it's still my tan, but notice that my opposite and adjacent sides switched. So now my opposite side to that 25 is 200 and my adjacent side is x. That green equation requires a little extra thought because I have to multiply out the x and then divide out the 25 or the tan 25. So no thought early requires a little extra thought to finish it. I don't care how you solve that equation, whether you have the orange or the green. I just want us to make sure that we're good in using one method. And then to be able to understand the other one. Regardless of how you get there, we clearly need to get the same answer. It's not like the distance to the cabin changes. There is no rounding rules in the question. That means I go back to my default, which means we round to 2 decimal places. And 428.9 is to 2 decimal places. Put on your units, make sure you've marked your rounding, and you are good. Okay, I'm hoping that that makes us feel pretty comfortable with angles of elevation and angles of depression. Okay, let's jump into another one. Okay, you see problem 3 on your page. What I want you to do, draw a diagram, but then I think we should be comfortable enough to finish this one off. So I want you to try to go start to finish on problem 3. Okay, pause the video now. Okay, we're back. So you're working your way through. I'm going to draw my diagram. It says the hypotenuse of a right triangle. So I'm going to draw a right triangle. There we go. The hypotenuse is 5 centimeters. One of the other sides is 1 centimeter longer than the third side. Find the unknown side lengths. So my tendency is to always want to make my variable, as much as possible, I shouldn't say always, as much as possible, I want to make my variable the smallest thing. That way I can build up to it. So we've already had that discussion. So I would be inclined to say I'm going to allow x to be the smallest side, and then the next larger side has to be an x plus 1. You could have totally made the longer side x, and therefore the shortest side x minus 1, but that just brings negatives into play, which means I have to be considering signs of things, and I get to avoid that with the purple. But clearly you can use either one. Okay. Question says, find the unknown side lengths. Now, I will fully admit that I think that this question was a little misleading with where I placed it, but it was done for good reason. Yes, I put a title on today that says Trigonometry Applications. And so you may have went, well, I guess I'm supposed to use trig on this. And so you spend your time trying to use trigonometry all the time. And I want to make sure that I can change an instinct for you. And it's something that we talked about in our trigonometry unit. Go back to basics. Remember, the reason I talk about grade 6 in bed maths all the time and grade 5 with division and factoring is not to make you feel bad about mental math, but instead to remind you, go back to old stuff and then build up from there. Don't fall into the trap of always using the most or the latest thing. So when I see a right triangle, my first instinct should be Pythagorean theorem. If I can't use Pythagorean theorem, then I'm going to SOHCAHTOA. If I can't use SOHCAHTOA, then I'm going to sine or cosine law. But I'm building up from my basics. So when you take a peek at that diagram, you should not be trying to force trig into it. No. Look, you have 3 sides of a right triangle labeled. I would hope that we were using Pythagorean theorem. So I could start off the problem saying, well, one small side squared plus the other small side squared has to give me my hypotenuse squared. And there is my application of Pythagorean theorem. That just built an equation in one variable. I am good to solve. Okay, if you hit a snag up to that point, then let's turn this problem into a mechanical one. And let's give us an opportunity to check and see how good are we with our mechanics. Work your way through, finish off this problem, do it on your own. Pause the video now. Otherwise, you're coming with me and we're going to expand our brackets and collect like terms. So I expand my perfect square. I can clean up the left side. I notice I will not be able to collect my x's, so I'm going to bring everything over to one side. First thing I look to do is factor. I do have a common factor, so I'm going to divide that thing out. Now I have a simple trinomial. Nice. Two numbers are multiplied to give 12 and add to give 1. And I get my solutions of -4 or 3. Okay. Now we take a peek at those solutions. Do they make sense for the application? Well, you go back, what was x? X was the smallest side on that right triangle, and clearly your smallest side cannot be negative. So I can get rid of that circle and simply label that as inadmissible. Okay, is it okay for the smallest side to be 3? Yeah, that makes sense. A small side of a triangle could be 3. It's smaller than the hypotenuse, so yeah, that makes sense. Okay, the question asks me, find the unknown side lengths. I found one of them. Now I need to find the other. I do not need to see you write sub x equals 3 into x plus 1, 3 plus 1, 4. Guys, I think that blue, it's beneath you to have to write and show. So if you are comfortable to simply take that x, look back to the diagram and see that, well, the other side would have to be x plus 1, so 3 plus 1, 4, then you are okay to jump straight to a therefore statement. Therefore, the other two side lengths, put on your units, 3 centimeters and 4 centimeters. And there we go. Hopefully good. I would love it if at the very beginning we never fell into the trap of trying to use trig. I'm hoping you were comfortable with going through that problem. Okay, one last one for today. Okay, I'm going to give you a chance to read problem 4. We're talking about a field goal kicker, and we're kicking the ball through the football uprights. Okay, you give it a read, and then I want you to try to draw a diagram to match. Okay, pause the video now. Okay, we're back. So, you may have, because we have a football field right behind our school, put a little extra detail into this one. Again, make your diagrams functional. So if you're like going on saying, yeah, but like there's the uprights, you know, I see them during gym class all the time, or I went to the foot. Don't. Remember, make it functional. So the question says a field goal kicker must kick the ball through the goalposts that are 5 yards wide. Okay, so if I was to draw from one post to the other post, this has to be 5 yards wide. Okay, the ball is placed 40 yards from one post and 36 yards from the other. Okay, if the ball was placed directly in the middle of those two, then the distance to both those posts would have to be the same. So what we have then is one post, another post. The ball has to be farther from one side than the other or closer to one side. So all I'm going to do is I'm going to put the ball a little bit on one side. The posts, this is horribly proportioned. The posts are a little close. Still bad, but whatever. 5 yards apart. A little bit closer, so I'm going to move that ball now a little bit. Closer on one side than what we are on the other. And there's my diagram. If this is the ball, then the problem asks me, what angle must the ball be kicked within to go through the posts? So if you have your diagram here, if that ball was kicked out here, then you're going to miss going between the posts. So what the problem asks for then is, what angle does it have to go through so that you make sure that when it's kicked here, it goes through the post somewhere. So if you're looking at my diagram, I need to find angle B. Okay, now that we have that diagram, we've turned it into a mechanical problem. You know you are looking for B. You have a chance to see, can you finish off that problem with the diagram? Okay, let's pause the video now. Okay, we're back. So you go through, now we got to figure out what angle. Well, I start early. Okay, is that a right triangle? No. So Pythagorean theorem is out the window, and so is SOHCAHTOA. That means I have sine law and cosine law. I am hoping that because we have all three sides on that triangle, we can go immediately to cosine law. But if not, then you are looking around that triangle and you're going, okay, I need an angle and its corresponding side. And because you don't have any sides inside that triangle, you cannot use sine law. Okay, then I'll use cosine law. And if you think about it that way, that's not that bad. Okay, I'm going to start off with cosine law, and I need angle B in there. So the version of cosine law I'm going to use has to start off with side B. Okay, if I was to write out like a formula, then I'd really want to have the other sides labeled, like maybe A and C just to create a triangle ABC. Well, then it would be the other one plus the other one. There's my Pythagorean theorem. Adjust it, cos of the angle. I do not need to see that red at all. Nor do I need to see your triangle labeled with the red. You could go ahead and you could just start using all that information right now. Okay, I'm going to sub in B, the side opposite my angle B. 5 squared, 25. Okay, my numbers are getting a little bit bigger here, so I'm going to now calculate 36 squared. That's 1,296. Then I'm going to calculate 40 squared. There's my 1,600. Okay, I need minus 2 of those two sides multiplied together. So my 40 times 36, double it, says subtract 2,880 cos of my angle. Okay, there is my blue equation. You can see your variable down there in the B. Now we need to isolate it. So I'm hoping that we're pretty comfortable. My recommendation to you in our unit was spend a line, clean that up. Now I could go ahead and I could isolate. If you are comfortable to get to this point, get rid of that and get ready to divide out that. Then we might be able to come in pretty quickly on, well, 25 minus 2,896 is, and you may choose to put this purple line in of negative 2,871 equals negative 2,880 cos B. But then when you see you're going to divide out that negative, really it just becomes a positive. So I will have a bunch of people that will like to jump to cos B equals 2,871 divided by 2,880. Okay, there is the exact value of cos B. Similar to our unit, you can skip this line of saying B is equal to the inverse cos. Please feel free to skip that orange. And I'm just going to wrap up right in here and go straight to an angle of B. Now, we're probably imagining something pretty small. So when I calculate 2,871 divided by 2,880, and then I take the inverse cos of that, I'm going to get approximately. Now, the question says no rounding rule in there. So we round to our normal rounding rules, which says for an angle, the nearest degree. I'm just going to jot up here. A decimal version of it would be like 4.53 degrees. So when we round that, we should be quite comfortable to come in on approximately 5 degrees. Okay, there we go. What you've worked through today: a few right triangles in terms of trig application, one where we don't make the assumption that we always need to use trig. And then lastly, there on your screen, you see there's an application using cosine law. Okay, your job, jump in, get as much practice as you can. Your diagram is so important. Don't fall into the trap, especially angle of depression. Don't fall into that trap when building your diagram. Okay, best of luck.